Every digital image manipulation, blurring, sharpening, edge detection, relies on a grid of numbers. As they change, the underlying frequency profile changes with them. We are going to analyze the mathematical behavior of 2D Finite Impulse Response, or FIR, filters, to see how these two domains interact. Our goal is to map how calculations performed on individual pixels dictate the behavior of the entire image across the frequency spectrum. We will start by evaluating a specific case from question 1, a 3x3 spatial filter. This specific filter averages its 4 closest neighbors, strictly excluding the center coordinate from the calculation. We need to find the specific mathematical link that converts these discrete spatial steps into a frequency domain equation. From there, question 2 asks us to analyze more complex filter matrices and verify their underlying mathematical properties. Specifically, we will test for a property called separability, a shortcut that simplifies how we process large two-dimensional arrays. Calculating the movement between these two domains allows for the precise design of filters that target specific visual artifacts. Let's focus on the mathematical definition of that 4-neighbor averaging filter from question 1. We begin with a 3x3 spatial matrix representing our input space, f of n, m. We isolate the center coordinate at 0, 0 from its immediate neighbors located top, bottom, left, and right. To compute a direct average of those 4 surrounding points, we assign an impulse response weight of 0.25 to each of them. Because the problem states we must exclude the point itself from the average, the center coordinate holds a 0 weight. This specific grid arrangement forms our discrete impulse response matrix, h of n, m. Looking at the populated values, you can see this creates a cross-shaped spatial kernel. By assigning a 0 weight to the center, this arrangement forces the filter to calculate its output based entirely on the surrounding spatial context. To understand how this local spatial context affects the signal, we use the 2D Discrete Time Fourier Transform, or DTFT. This transform sums the product of our spatial matrix values and complex exponentials over the grid coordinates n and m. When we plug in our matrix, the 0 values drop out. We are left with the 4 active spatial terms, each multiplied by their 0.25 weight and a corresponding complex exponential. We group the mathematically symmetrical spatial terms together along the horizontal axis, omega-1. We do the same for the vertical axis, omega-2. We can simplify this expansion by applying Euler's identity. Euler's formula allows us to convert those complex exponential pairs directly into standard cosine functions. The 0.25 weights combine, giving us a multiplier of 0.5. This yields the final frequency response equation for our question 1 filter. H of omega-1, omega-2 equals 0.5 times the sum of cosine omega-1 and cosine omega-2. The 2D DTFT maps a 4-point spatial average into a continuous trigonometric expression, defining exactly how this filter responds to any input frequency. With the equation derived, we can determine whether this acts as a low, high, or bandpass filter. We test the equation at the DC frequency, the 0 frequency origin point, where both omega-1 and omega-2 equal 0. This is a 3D surface plot of our derived equation. When we evaluate the response at the origin, the 0 values plug into the cosine functions. The cosine of 0 is 1. The two cosines sum to 2, which is then halved by our multiplier, resulting in a maximum gain of 1. Unity gain at DC means that constant uniform regions of an image will pass through this filter unchanged. Next, we evaluate the response at the highest spatial frequencies, locating the boundaries at coordinates like pi0 or 0 pi. At these extremes, the cosine of pi evaluates to -1. The terms negate each other, driving the output to a gain of 0. Because the filter passes the lowest frequencies with unity gain while blocking the highest spatial frequencies, it operates as a low-pass filter. This brings us to question 2 and the filters designated as H1 and H2. The condition for separability is that a 2D filter matrix must have a rank of exactly 1. A rank 1 matrix can be mathematically factored into the outer product of 2 distinct one-dimensional vectors. The isolated column vector represents a dedicated vertical filter, H1 of n. The isolated row vector represents the dedicated horizontal filter, H2 of m. Applying a separable 2D filter is mathematically identical to filtering the data horizontally and then filtering that result vertically. Our cross-shaped filter from question 1 does not have this property. Because of its diagonal zero values, it is rank 2 and cannot be factored into 1D vectors. Identifying separability is a key optimization. It reduces the computational requirement from n-squared operations down to 2 simpler n-length operations. Spatial separability also simplifies finding the overarching frequency response. For a separable filter, the 2D frequency response is the direct product of its 2 independent 1D frequency responses. The absolute maximum point on the resulting surface occurs where both 1D components reach their peak simultaneously. We can also map the 0 points by looking at each 1D component. The topography follows a multiplicative rule. The overall 2D surface response hits 0 wherever either of the underlying 1D components equals 0. Every peak and valley of this spectral topography is a direct consequence of the spatial arrangement of the filter matrix. Comparing these two results highlights the difference between a general 2D kernel and one that can be decomposed into 1D steps. Exploiting properties like separability reduces the computational burden of 2D signals to the level of 1D processing, allowing for real-time image manipulation.